there's an Albert Einstein quote out there that compound interest is the most powerful force in the entire universe, uh, which is sort of cute, but correct. This way of calculating interest is how banks do everything. Whether you are borrowing the money or you are investing the money, interest is not just a simple percentage of what you take or give. It gradually grows each month that you leave it there, so that you end up paying interest on the interest on the interest until the loan is paid off. So I'm just going to tear this apart. First, I think the basic idea is that this thing is going to turn out to just be a geometric sequence. So we're going to have to figure out how to turn this formula into something that fits a finance question. Okay, so suppose you borrowed $12,000 to pay for your first year of university. The bank offers you a rate of 6.3% compounded monthly for a 4-year term. So there are a few words in there we've got to figure out. This one here first, compounded. Oh, and there is a phrase I want to put in here. Per annum. 6.3% per annum, compounded monthly. So first off, compounded is the number of payments you make in a year. So how many times is the interest applied in a year? In this case, if it's compounded monthly, that means it's applied 12 times in 1 year. Okay, this second phrase here, per annum. Annum is Latin for a year. It comes from the root word for circle. So if you've ever heard the word annular, right, that's A-N-N-U, that the prefix means something that is around. Okay, actually, yes, it's Latin for ring, actually, not circle. Circle is circa. Doesn't matter. We'll fix that later. Okay, so per annum, that is per year. So in this particular case, 6.3% per year is the rate the bank is quoting you, but that is not how they're going to charge you. They're going to take that interest rate per year and they're going to cut it up into 12 pieces. So combined, the actual rate you're going to be paying in interest will be the 6.3% that you were quoted divided by 12. So first thing we got here is a percentage sign. So 6.3% is just a fancy way of writing 1 over 100. So I'm going to have to take 6.3, divide it by 100, and then divide it by 12. Let's see. 6.3 divided by 100 divided by 12 gives me 0.00525. Per month. Okay. Good. So once you're quoted a compounding period and you're quoted an annual rate, you can use those two things to figure out how much interest is charged in each compounding period. Last word we're going to need up here is term. And term is how long the loan lasts. So that's the length of the loan or investment. And in this case, it does say 4 years up there, but 4 years is not the number you're going to use. You have to quote that term in compounding periods. So it's the length of the loan or investment in compounding periods. Sorry, you're having to watch me write. I know it's not very interesting. So in this case, it was a 4-year term. It says right there, 4-year term. But it's being compounded monthly, which gives us a grand total of 48 compounding periods. Okay. So how are we going to shove all these numbers into that equation? Well, if you think about this loan, you take the $12,000 and then you're going to have to multiply it by this. Now, if you do 0.00525 times 12,000, you're going to get, well, we might as well do it. You get $63. Now, that's just the interest. So I want to know how much I owe after the first month. I don't just want to know the interest, because I'm not just paying back the interest, I'm paying back the whole thing. So in here, I have to be multiplying by 1, because 1 will keep the $12,000 I originally owed. And I need to add in addition to it 0.00525. So I would have to do 12,000 multiplied by 1.00525. Again, why 1? Because at the end of this month, I don't owe $12,000 anymore. I owe $12,000 plus some extra. So I need that 1 there to make sure that the $12,000 I originally borrowed propagates through the calculation. Now, if I left this for a month, I would apply that interest once. If I left it for 2 months, I would apply that interest twice. If I did it for a year, I would have to apply that interest 12 times. So I'm getting that exponent up there, just like I did in my geometric sequence. So I'm going to start changing some stuff up here. My $12,000, there is a word for that. That is the principal. Not principal. This is a set of beliefs or values that you put first. This is amount of money or some other object that you put first. This is a sort of theoretical idea. This is a real thing. Like the principal at your school is not a set of high-minded ideals. The principal is a literal object that's sitting in an office somewhere. So they are the principal, not the principal. Anyway, this is not a grammar lesson. That principal is the thing that we started with first. So that was my first term in the sequence. I'm going to put a P there. Second thing I've got is this, my R value is 1 plus the adjusted interest rate in terms of compounding period. And then the exponent up here is the number of months I leave it around. Now you might be asking, why is it n and not n minus 1? Well, this sequence would start as 12,000, then 12,063, ... And we would have called that term 1, we would have called that term 2. But this is not how much you owe after a month. This is what you put in at the beginning. So I haven't had any time go by on this term. This is actually term 0. Right? 0 interest has been applied to it, which makes this term 1, which is going to bump all of my terms up one value. So I can get rid of the minus 1 there just to make it simpler to deal with. Okay, all that together is going to give you the total amount that's worth. I'm going to use a T. Sometimes they use an A. Sometimes they call that future value. Sometimes there's lots of different letters you can use there. I think we used A as the first term in all the sequence stuff, so I'm just going to avoid that letter so it doesn't become confusing. So just a big T for total. Write that in there so you can see that total. All right. Well, the term here wasn't 1 year. The term was 4 years. That's 48. So what is the total we're going to owe for that first year of university? Well, I have to do 1.00525 to the exponent 48. And I get 1.285748201. ... Sure, there are more decimals, but my calculator doesn't show them. Now, you're maybe used to rounding off at the second digit, third digit, fourth digit. Normally, that's okay, but we're going to be multiplying this thing by something in the 10,000s, which is going to move the decimal place 1, 2, 3, 4, somewhere here. So if I don't keep all of the decimal points, I'm going to end up rounding actual dollars and cents. So because this is in the context of money, and you need to keep everything up to 1/10 of a cent to be accurate, you can't round this. So you park that all into your calculator, you get this obnoxious decimal, and you just hold it on the screen there and type times 12,000, and it will give you an unrounded answer. So I end up with $15,428.98. So there's the catch, right? A bank is willing to give you the money to fund your first year of university, but when you go to pay them back, you're going to have to pay them back an additional $3,400 in order for the privilege of being able to borrow that money. Okay, so I'm going to clean all this mess off here and we'll do a different example. But just to sort of think about this formula up here, we just did a question where you knew P, you knew I, and you N, you were trying to get the total. So there's 3 more types of questions you could ask. If you're solving for P, it would be how much money would you have to put in the first place? That feels more like an investment question than a borrowing question. You could solve for I. That's like what interest rate would you need to turn this into this? That feels more like an investment question, less like a loan question. And then N would be how long are you going to leave it there? So that could be either, right? What will you owe if you leave that loan for 10 years instead of paying it off in 4 like you should have? Or how much will this investment be worth if you leave it for 40 years before you retire? So I'm going to clean this off. We're going to try one of each of those examples, and then I think it'll be good for the word problems. So we've got a new question here. Suppose you would like to have $2 million to live off of when you retire at 65. which for you, if you are in grade 11, will be 58 years from now. Feels like a long time. That's because it is. How much money must you invest today at 5.7% per annum compounded monthly to make this happen? Well, I'm trying to fill in here. So I have a total amount this time. I know I want it to add up to $2 million. So T is 2 million. And then it feels like a lot of zeros, because it is. I don't know how much I'm putting in the first place. That is what I've been tasked to find here. My interest rate, the first thing I was told that it was 5.7% per annum, which equates to which is 5.7 divided by 100, because that's what that little symbol means. Gives you 0.057. And then it is compounded monthly, so I'm going to have to take that 0.057 and divide it by 12, because I'm only applying a piece of that interest every month. 0.057 divided by 12 gives me 0.00475. Right? And my term is 58 years, but I have to express that in terms of compounding periods. So if it's compounded monthly, that means it happens 12 times in each of those 58 years, for a grand total of 696 compounding periods. All right, so I have a formula there. So in it goes, $2 million is the principal amount multiplied by 1 plus 0.00475 to the exponent 696. .00475 to the exponent 696. All right, so I'm going to have to get my calculator to do this obnoxious thing. 0.00475 to the exponent 696 gives me 27.063150005 ... I mean, we're not done, but if you take a look at this, 5% increase doesn't feel like a lot, but when you do when you let it work for this long, you're going to end up with 27 times your initial investment, which, I mean, that's pretty remarkable. So to finish this off here, I just have to divide my $2 million by that number. 4, 5, 6. This is just standard algebra rules here. And my final answer, denominator, is 2, 1, 2, 6, 5, 6. Gives me $73,901.23. All right. So that interest rate right now, that's not an unreasonable interest rate to get on some kind of investment. I think it's not even a remarkable interest rate. You could definitely find that if you manage your money correctly, or can find someone to manage it correctly for you. And if that's true, and if you've got this much time to do it, all you need is about $74,000 right now in order to grow that to 2 million by the time you turn 65. Now, who has $74,000 lying around? But the idea is you can put money away now and then live off it later. And that's the entire idea behind pensions, or your CPP, that is a pension plan. Even if you don't have $74,000 lying around right now, you can do a monthly plan. That's a thing called an annuity, and we'll be doing that in a bit. But there are vehicles available for you to turn what are manageable. I apologize for calling $74,000 a manageable amount of money, but it's a manageable amount of money compared to that. So if you ever received an inheritance, or you happen to get OSAP money and you wanted to invest it, right? Like OSAP funds or inheritances tend to be on the scale of this number, not maybe that big, but in the tens of thousands. You can turn tens of thousands into millions with enough time and enough interest rate. Okay, so I'm gonna clean this off and we'll try a different example. Got a new type of example here. So how long would you have to leave a $17,000 investment in an account paying 7.8% per annum, compounded monthly, for it to grow to $500,000? Which at this moment in time is probably enough to buy you a house in the place where I live anyway. Okay, so in this particular question, I know how much I have for principal. I know how much I'm going to put in. I know how much I want to get out, and I know how the account is paying. So the thing I'm missing then is the number of compounding periods that have gone by. So I start with my formula. Well, I should probably get the interest rate figured out first, shouldn't I? Okay, so my interest rate was 7.8% compounded monthly. That's 7.8 divided by 100, which is 0.078 per year. 0.078 compounded monthly, I have to divide that by 12. So 0.078 divided by 12 gives me 0.0065. So I have that number now. It's been adjusted for my compound period. I can put it in there. So I want $500,000 out. I'm going to put $17,000 in. And the I value will be 0.0065. And I don't know N. Okay, well, first things first, I can do that little addition in there. Gives me 1.0065 to the exponent N. I need to get this number off the front, so I break that with division. And 500,000 divided by 17,000 gives me 29.4117641 ... So again, we're not done, but if you look at that line, basically what this question was asking was how long are you going to have to wait for this interest rate compounded monthly to make your initial investment increase by a factor of 29.5. Okay, so we have to do a little bit of fancy footwork here, because if you have a variable in the exponent, you need a logarithm to break that. So I'm going to need to do log of both sides. I'll carry away there. You stay down there, you go up there. So if I divide this logarithm by that logarithm, I should get my final answer. So I need log 29.41176471 divided by log 1.0065, and that's going to give me n. All right, so my calculator here. Log of 29.41176471 divided by log 1.0065 gives me 521.9. 500 years, they cried. That's impossible. Well, right, agreed. But that's not 500 years. That's 500 compounding periods. And so in the context of this question, 500 months, 521 months is what we're after here. So to actually convert that to years, because I don't know how long 521 months is, I have to divide that by 12. I get 43.49 years. Okay. So if you manage to find something paying this interest rate, which I think if you're a clever investor, you can get something around that per year, and you have $17,000 to invest, in 43 years from now, you're going to be able to have $500,000 sitting around. Now, what can you do with that information? Well, 17,000, that is an accessible amount of money for most people if they are disciplined savers. That's $1,000 a month for a year and a half. So if you can manage to gather that money up, and you were investing it, just put it away and then forget that it's there. 43 and a half years from now, which would make you 60-ish when it's ready, would spit out $500,000. Now, if you bought a house at some point in those 43 and a half years, you probably haven't paid it off yet, but now you can. And once you clear out all that mortgage debt, now retirement becomes an option for you, because most of the money that you end up working for in your life is to pay for your living expenses. So if you've got this little nest egg building up, as soon as it's big enough to wipe out your mortgage, then your entire lifestyle can change. So how long would you have to wait for that? Well, you could figure that out and then make some plans for the future to know if you could retire early or if you're going to have to work a little longer, etc. So we have one more question we have to answer. We have to answer an I-type question. So I'm going to clear this off and construct one for you. Okay, this one's got some funny wording and not a lot of numbers. So what interest rate do you need to double your money in only 10 years? Now I'm gonna park in a little assumption here. Let's go compounded daily. Not that interest is generally compounded daily, but just so you can see an example of something that is not compounded monthly. It's not everything is a monthly payment. Car payments, for example, tend to be bi-weekly. Rent is monthly. Credit cards compound daily. That's why they're so dangerous. All right, so what interest rate do I need to double your money in only 10 years if I'm compounding daily? Well, I don't know how much I'm putting in. and I don't know how much I'm getting out. But based on the phrasing here, the amount that I get out has to be twice what I put in. So I'm going to put this into this equation here. So 2p would be p 1 plus I to the n. My p's are going to divide out. I'm left with this. All right, 10 years. 10 years compounded daily. And there's 365 days in a year. 365.25 if you want to be super precise. That means that my compounding period will be 3652.5. So if I put that in there, I have a number up in an exponent and a variable in a bracket. I need to use a radical or a fraction exponent to undo this. So I need the 3,652.5th root of 2. That sounds really stupid to say. Give me 1 plus my interest rate. So you find your generic root there. And it will allow you to enter decimals. So let's go 3652.5 root. That's my generic root of 2 gives me 1.000189.791 ... And I just have to subtract 1 from both sides, giving me 0.000189.791 is my interest rate. That's a very small number. But again, it's sort of like the last example. This number that comes out at the end, this is per compounding period. So I have to adjust that back up to a per annum rate. So if it's this much per day, and we said there were that many days in a year, I'm going to have to take this and multiply it by 365.25 to get how much I'm paying or earning, sorry, in a year. Minus 1. 365.25 gives me 0.069321295551, which is approximately 6.93% per annum. Okay, which is right in the neighborhood of all the examples that we just did, right? Somewhere in the 5 to 7 range, 5 to 8 range. This number here was just a good rule of thumb for whether an investment has been worth it or not. You should be expecting to double your money in about a decade. And if you're able to do that, then the investment you're making is a good one. It's a pretty standard. That's kind of the expectation when you're investing money. And so the magic number then is 6.93% per annum. If you have a portfolio that is doing better than that, then that's good. If it's doing less than that, then you should probably consider switching where your money is. Okay, so that's an example of how to solve for T, for P, for I, and for N in the compound interest formula. So you should be good to go for the practice problems.